Hello friends, welcome back to tutorials. Our next topic is pumping lemma. Pumping lemma states that if L is a regular language, then there exists a constant n which depends on L, such that for every string W in L whose length is greater than or equal to n and which can be broken into three parts x, y, z, such that W equals to xyz and y is not equal to empty string and length of xy is less than or equal to n, then for all values of I greater than or equal to 0, the string x y raised to power I z also belongs to L. Now let us prove this lemma. Suppose L is a regular language which is accepted by finite automata M. It means the language of finite automata M is L. Suppose M has n states. Right? There are n states in finite automata M. Now n is the constant which depends on L. Now there is a string W which is equals to A1, A2, A3 up to AM. Now here A1, A2, A3, A4 up to AM are input symbols. Right? Here M is greater than or equal to N, which means length of this string is greater than or equal to N. Right? Now suppose when we apply a string A1, A2, A3 up to AI to the initial state of automata M, then automata jumps to state QI. It means when we apply a string A1 to initial state Q0 of state M, automata jumps to state Q1. When we apply a string A1, A2 to the initial state Q0 of automata M, it jumps to state Q2. When we apply a string A1, A2, A3 to the initial state Q0 of automata M, it jumps to state Q3. So in this way, the sequence of states through which automata M passes after reading this string A1, A2, A3 up to AM will be Q0, Q1, Q2, Q3 up to QM. Now this sequence has M plus 1 states where M is greater than or equal to N, and N is the number of states in finite automata M. Since the number of states in this sequence is greater than the total number of states in finite automata M, these all states cannot be distinct. Right? So let the two states Qi and Qj are same. So it means now we have divided the string W, which is equals to A1, A2, A3 up to AM into three parts x, y, z. Substring x will drive the machine from its initial state to Qi state, and substring y will drive the machine from Qi state to Qj state. And I have already told you that we have supposed Qi equals to Qj. Right? It means machine will jump from Qi state to Qi state on reading substring y, and reading the substring z, machine will jump from Qi state to Qf. That is the final state. So this string will be accepted by this finite automata. Now we have to prove that x y raised to power I z for all values of I greater than equal to 0 will also be accepted by this finite automata. It means x y raised to power I z for all values of I greater than equal to 0 also belongs to the language L. So when I equals to 0, the string will become xz. So xz will be accepted by this finite automata. How? First of all, it will read this string substring x, and after reading it will move to qi state from initial state, and from here it will read z and move to final state qf. If I is greater than 0, m first goes to state qi after reading substring x, right? And from here it will circles from qi to qi I times, and after that it will read z and move to state qf, which is the final state. So in this way x y raised to power iz will also be accepted by the same finite automata for values I greater than 0. So it implies x y raised to power iz also belongs to language L. So we have proved this pumping lemma that if here xyz is a string of language L, then xy raised to power iz for all values of I greater than equal to 0 also belongs to language L, where the length of a string xyz is greater than equal to n, and y is not equal to empty, and length of xy is less than equal to n, where n is a constant which depends on language L. Thank you very much. Pumping lemma is used to prove that certain languages are not regular. It is used to prove that a particular language is not a regular language. It is never used to prove that a language is a regular language. Now, how can we prove that a particular language L is not a regular language by using pumping lemma? First of all, take any constant n which depends on language L to whom we are going to prove non-regular. Then take any string which belongs to language L whose length is greater than equal to n. Now divide it into three parts x, y, z such that y is not equal to empty string and length of xy is less than equal to n. Now prove that x y raised to power iz doesn't belongs to language L for some value of I greater than equal to 0. Now we are given this language L, which is a set of strings of form a raised to power m, b raised to power m, and value of m is greater than equal to 1. Now we have to prove that this language is not a regular language. First of all, I have chosen a constant n. N is the number of, first of all, I have assumed that this is a regular language, right? Now I have chosen a constant n. N will be the number of states of a finite automata which will accept this language. Now second, I have chosen a string a raised to power n, b raised to power n. Here the length of this string is greater than n. Now there are three ways to divide this string into xyz. First is when y is made of entirely a's. Then if y is made entirely of a's, then y is not equal to empty and length of xy will also be less than equal to n. So these all conditions of pumping lemma are satisfied. Now I have to prove that x y raised to power I z doesn't belong to L for some value of I greater than equal to 0. Now here y consists of only of a's. Now when the power now in the string x y raised to power I z, when the value of I is 2 or greater than 2, then the number of a will exceed the number of b's, right? In that case, the string x y raised to power I z will not belong to language L. Now second case, when y is made of entirely b. Now then also these all conditions of pumping lemma will be satisfied. Now I have to prove that x y raised to power I z for some value of I greater than equal to 0 doesn't belong to L. Now again here y is made of entirely b's. When the value of I is greater than or equal to 2, then number of b's will exceed the number of a's. Here then x y raised to power I z will not belong to L if the value of I is 2 or greater than 2. Now third case, when y is made of both a and b. When the power of, now again all three conditions of pumping lemma are satisfied when y is consist of a and b. Now here when the value of I equals to 2 or greater than 2, what will happen? Now first of all consider when the value of I equal to 2, what would be the string x y raised to power I z? Then it would be something like this. First of all there will be a, then ab, and then b, right? So what will happen? First there will be a, then we have here the power of I is, here the value of I is equal to 2 in this string x y raised to power I z. I equals to 2, so the string would be x y y z. So the resultant string would become a, then ab, and then b. Now this string will not belong to L. This string doesn't belong to language L. So this language is not a regular language because it does not satisfy the condition of pumping lemma, that is x y raised to power I z should also belong to L. So it is not a regular language.